Thank you, everybody, for raising your hands when you were commanded to, and for reading those papers. Yeah, so in my abstract, I said that I was going to talk about modeling, but it occurred to me that that was a little ambiguous, and I meant mathematical modeling, not fashion modeling, although some of what I say at the beginning will apply to both. So there seems to be a lot going on in using math to model things. There's especially a lot of topology getting used for things in data science and in biology. And today I want to talk about, let's see, so what's up with this? I can erase that. So today I want to talk about some joint work with Dan Fried. So I'm going to be giving 4 lectures, and they're actually related. So the first 2 are going to be joint work with Dan Fried. Using what winds up being some computations in stable homotopy theory to classify topological phases of matter, which was a classification scheme initiated by physics, and physicists, and some parts of it were done using physical methods, and we were able to kind of come in and correct some things and complete the calculation. So it really is an actual application of like computing stable homotopy groups to things people in the physics world really wanted to know. So when you picture mathematical modeling, you think of Faraday sitting in his office or his home, with a table and a magnet underneath the table. Let's see. I have to draw magnetic lines. A magnet under the table and metal filings on top, and these filings are pointing in different ways, and he's moving the magnet around, fooling his kids into thinking he has magic powers or something. And then there's these lines of force, and then you imagine that Faraday looks at this and goes, oh, well, that's just a vector field and a one form, and then we'll model the math that way. But that, even if you look and read Faraday's papers, isn't really how things work. I mean, there's kind of a kludgy model that comes in, and then the math is adjusted, and then the physical thing is adjusted, and there's a kind of feedback loop between the math and the thing you're modeling. Okay, so it's math or theory, let's say. So there's a sort of feedback mechanism. And this is the part that actually applies, I think, to fashion as well as math. I mean, you can have this whole there's theoretical clothing, and then it actually has to fit on actual people, and there's a sort of feedback loop that I think changes what people wear and how people design clothes, whatever. Okay. So there's a feedback mechanism here that's really, to be involved in it, and I want to tell you a little bit about how this worked in the case of where we were applying homotopy theory, but it's really useful. It's nice to bear this in mind and to think of other examples of this. So often, so there's even sort of different terminology for the math for math, okay. I did it 4 times and I didn't get to all the, no, oh, there we go. I really have a magnet under the table, that's how I'm doing it. So there's hook. Okay, right, sorry about that. So there's even some terminology that's kind of helpful in guiding. So when you're doing modeling, there's something called a model. Duh. But a model that's something we don't quite have a name for in math. A model is like a little gadget. It's like a little bunch of math things that you're trying to use on something. And in fact, this came up in Gabriele Vezzosi's talk. He talked about the Landau-Ginzburg model. And somebody asked, well, what is a Landau-Ginzburg model? And he just said, it's just, and he didn't have a word for it, right? It was just a function from some scheme or some stack to A1. And, but it was that data, that's a little gadget that people, I mean, Landau and Ginzburg used it to model, well, things like this connection with matrix factorizations. And it's a little mathematical gadget that people try to use to model different things in science and physics. And that one bothered me. I remember a few years ago, people were always talking about the Landau-Ginzburg model, and I had exactly that same question. I was like, well, what is it? And everyone would just describe this setup. And I go, no, like, is it a theory? Is it a manifold? What is it modeling? And no one could ever answer that for me. And I finally had to realize that when math is designed to model something, there's a term that they use, they call a model, for just some mathematical gadget that you think you can use. And it's not really a theory, it's not a structure, it's just something. So that's one word that gets used a lot, a model. And another is this term you probably know, ansatz, which I'm probably going to spell wrong, this is a really bad place to be spelling this wrong. But an ansatz, that's also, it's not quite a hypothesis. It's not that, an axiom. It's not something we have an analog of in pure math, but it's just a guess that some structure in math is actually going to model some structure that you're staring at. So this is one thing I've enjoyed in getting involved in this kind of, in this world, is sort of just recognizing that the intellectual structures we use, they're really different if your goal is to think about pure math or your goal is to think about math as modeling something. So that's one thing. And another example of a model, I won't write these things on the board, but there's topological quantum field theories, which I'll be talking about later, those model things. There's the sigma model, which you may have heard of in physics, which is you have space-time and some function from it to some space of states, and it's really just, there's a lot of different ways of thinking about it, but it's really a gadget, not a theory. And these models, they get recycled and reused a lot. So the model of a topological quantum field theory was intended, I mean, at first it was just an abstraction away from the physical models coming up in string theory to things that were purely topological, and it was used to explain some knot invariants and Donaldson invariants, and it didn't seem like it really, it emerged as kind of supporting cast in some physical theories, but it didn't look like it at the time that it was really useful for modeling something. And in recent years, people started to use topological field theories to model things in condensed matter physics. So I'll say more about this in a little bit, but the basic idea is that you have some kind of material you're studying, and its behavior below some certain energy, there's a lowest energy state it can occupy, and below that, it can't change. So picture like you're cooling water down and it becomes ice. But imagine that ice could take on different forms. I don't mean forms like, oh, it could be an ice cube or it could be an ice snowman. I mean, it could actually like really be different. And that low energy state, that used to be regarded as uninteresting, and now it's regarded as very interesting. And those states, that's something that doesn't deform as the energy changes a little bit, and those are classified by, we think, topological field theories. And that's sort of the classification, that's the computation Dan and I did. And anyway, I want to tell you a little about it. Okay, so but let me kind of BS on a little bit more before I get to, okay. I wish there were more of these, only because then I would have an excuse for having tried so many possibilities and still not succeeded. So there's something else I want to illustrate that I've been spending, for some reason, a lot of time escaping into the 19th century because the 21st century seems so horrible lately. But one of the things I've gotten kind of obsessed with is learning about the history of thermodynamics, and there's a lot of important things about modeling there. So in thermodynamics, people were building steam engines, and they needed to figure out how they worked and how to make them more efficient. And in a typical thermodynamics story, you might have a piston, maybe, and this piston might be, it's trying to move in this direction, and maybe it's driving, there's some, it's fastened to some wheel that it's turning. And there's a heat source here. This is going to be so people didn't use candles, right? They used giant coal or wood or whatever. Anyway, there's heat going in, and there's this gas in here heating up, and it's pushing the piston, and it's converting heat energy into mechanical energy. And in the early days, they didn't know what heat was. They knew it could be converted to mechanical energy, but there was a theory that heat was this fluid that entered substances and could leave it. And this fluid was called the caloric. And we still use that word for other things now, but the heat was this caloric entity, and they tried to. There were terms. There was the cost of the energy being used. So there were terms like heat, pressure, volume, temperature, which was different than heat. And there was a mathematical theory that kind of got put together largely by industrialists and some scientists that expressed a relationship between these things. And it was built on, there was a theory, but it wasn't directly connected to explaining why, when you heat this up, pressure increases and the wheel turns and all that. It was just people were making observations. They were building a mathematical model, and but it was there to explain some experimental observations. It wasn't derived from a theory of what constitutes a gas, what happens when you're heating it up. And of course, as we know, towards the end of the 19th century, this theory, which had been in debate for 100 or more years, that gas was really made up of molecules, and these molecules were moving, and that this effect was just an average effect of Newtonian mechanics applied to these molecules. So that theory and the sort of development of these equations was from the work of people like Maxwell and Boltzmann and Gibbs and all these names that you learn about when you're studying this. They sort of figured out how to derive these properties from an aggregate of Newtonian mechanics applied to all these little molecules floating around. Well, I kind of like this picture. This is sort of a steampunk version of what's happening, how you can think of condensed matter, of this relationship with condensed matter physics. And it's surprisingly appropriate for where we are today in some of this. So in this world, in condensed matter physics, you have some material, and so this is in condensed matter physics, and it's got a bunch of electrons whose states are bound by some rules, and they're moving around a little bit, and there's various fields describing this. But ultimately, you have something that's described on a whole bunch of points of sites, which is called a lattice. You have some lattice, some huge lattice of states of things, And this is the system that you want to describe. And that's like knowing thinking of gas as a bunch of particles and trying to deduce thermodynamics from the molecular theory of gas using statistical mechanics. And in this case, in the physics, there's this lattice models, and then there are topological quantum field theories. And it's kind of funny, when you go back and you read about statistics, if you're a mathematician and you read about thermodynamics, it's sort of hard. It's hard to get your mind around, probably because we're not as exposed to steam engines as we used to be, but it's hard to get your mind around entropy, enthalpy, heat, pressure, all these terms that were used to describe what's going on in a system like this. And these are called, in modeling, these are called emergent properties. The model, I guess, nowadays, we would think of this as a large aggregate of small Newtonian systems, and these are the emergent properties. But in this relationship, this notion of a topological quantum field theory, that's the emergent property. I guess to most people, it's probably harder to learn about topological quantum field theories than it is to learn about heat, pressure, volume, and temperature. But we're weird, and it's the other way around. So for us. Anyway, this is something that we think of as a sort of nice, sophisticated, rich mathematical theory, but we don't really know how. So in principle, this is supposed to be an emergent properties that emerge from some statistical understanding of the molecules and the electrons in some material. But this is, so where we are, it's like we've had Joule and Watt and Carnot and those kind of people, that contribution, but Maxwell and Boltzmann and Gibbs and the sort of beginning of statistical mechanics hasn't quite happened. So we have this, it's predictive about this, but we don't really know how to go from a lattice model to topological quantum field theories. So I mention that because, so there's supposed to be a loop mechanism here, and there's a lot of exciting current work being done by people like Anton Kapustin, Alexei Kitaev, and others that are looking for lattice models of things like principal G bundles and connections and Chern classes and all the kinds of stuff that we learn about in topology. There's a little bit of an industry of trying to see how those can be emergent structures that come out of lattice models. And anyway, I just wanted to advertise this early on in this talk, that there's been some success in this relationship in the sense that we have computations that are both predictive and corrective, but this story is far from being understood, and there's a big arc of research that goes into trying to really derive this emergent structure from lattice models. And this is a very interesting and very difficult area right now. Okay, so that was a kind of long-winded introduction, because I know from watching yesterday's talks that this 50 minutes that this talk takes goes by real slow. So let me try to dig into. Oh yeah, speaking of which, okay. So let me now get into some more concrete mathematical things. So I'm going to give 2 talks on this and 2 talks on a closely related but very different sounding topic for my last talks. So what are the emergent features. How do you know when you have, when you're staring at something like a topological field theory? Well, the fundamental emergent features are locality and unitarity. So locality is supposed to say there's really a lot of these lattice points, and even though I'm supposed to add up something for every single one of them, you know, if I broke this up into a bunch of tiny regions, there's about as many in each of these regions as there is in the whole thing, and I have some sort of mini theory here and a mini theory here, and I can understand the whole theory by looking at some effective theory for this region, something for this region, trying to understand the interface between them, and then get the whole theory to emerge. So the idea is that you can assemble something at a larger scale by patching together things at a local scale. So that's what locality is. In unitarity, that's harder to explain, but it says that an evolution or a state in the evolution in quantum mechanics comes from the action of a unitary operator. Now, in setting up the mathematics, we've gotten very good at modeling locality, and unitarity is something that hasn't been implemented as well. And that's part of the feedback loop that I'm going to talk about a little bit today and more tomorrow, is how we come to grips with unitarity in this world. But let me talk about locality. So for that, I want to talk about this notion of a topological quantum field theory. So what's a topological quantum field theory? So that's something that has a dimension, so of dimension n. All right, so we have so a topological field theory is something I'll call Z, and it associates to every n manifold a complex number. And you're trying to calculate this complex number. But you're trying to do it locally. So the manifold might be this slab I've written, or maybe this slab is, it might be that. It might be that. Sorry, I don't have anything else to say about that. So, okay, so we're supposed to imagine that this manifold, maybe we're going to cut this manifold up into two pieces, and we want to calculate this number from some sort of an interface. So maybe the manifold looks like this. I'm trying to make a calculation here, make a calculation here, and assemble them along some interface. And so there's more data. So we would associate to an n-1 manifold a vector space. And how is this? So the empty manifold gets the zero space. So more generally, if I have a cobordism between manifolds, then this should be a linear map. Now you might think, and it might be a good idea, that we should require these vector spaces to be Hermitian and this linear map to be a unitary map. And eventually I'm going to make an ansatz that some structure we're looking at in topology models that, but it's not really obvious how to put that in. So this structure does a good job of describing locality, but not yet unitarity. And remember, in my picture of that slab, I cut it up into regions like this, right? And so these things have corners in them. I'm not just looking at codimension 1 interfaces, but there could be contributions from codimension 2 interfaces. So I might have something like, well, let's see, I might be, let's see if I can. I sort of forgot how this picture goes, but And I might have something like that, something with corners where there's topology change as I move around it, and we would want to associate some structure to that to express locality. So a topological field theory is somehow this data. And this, we've had a lot of success with, all right, here we go again. Nope. We've had a tremendous amount of success in understanding what a topological field theory is. So let me give you a more formal definition. So more formally, what do we say? We introduce this. So more formally, we'll make some, I'll call this, I'll start with some space X and some vector bundle over X of dimension n, of real dimension n, a real vector bundle of dimension n over X. And then we'll define board nx to be the infinity n category so this is the infinity n category whose k-morphisms so the k-morphisms are a manifold M of dimension k, but that's a manifold with corners like this. Equipped with, I didn't prepare my notes this way, but never mind. It's going to be more convenient to have this index be the codimension later on. But we'll just go with this. So a k-morphism is a manifold of dimension k with corners equipped with a map to X and an isomorphism of the pullback of V with the tangent bundle of M bumped up to have dimension n. All right, and that's an infinity n category. I have cobordisms as maps. I have diffeomorphisms of manifolds. And it's symmetric monoidal under disjoint union. And yes, Virginia, this symmetric monoidal infinity n categories are easier for me to think about than heat and enthalpy and pressure and volume. I don't know why, but they are. Okay. All right, so that's what, and a topological field theory that's a symmetric monoidal functor. I'll just call that a functor. So it's symmetric monoidal from board n x to some other C, where C is just another symmetric monoidal infinity n category. All right. And that really remarkably effectively captures this locality notion. So the examples of X that you should have in mind are sorry, I can't seem to talk and erase at the same time. The examples of X's that you should have in mind are like X is a point, in which case you have your manifold is framed if it's of dimension n and stably framed if it's of dimension lower than that. And so that's called board n framed. And other examples are X is B spin n, in which case our manifolds would all have spin structures, or BSON. If it's BON, they don't have much structure, additional structure at all, except that that vector bundle was of dimension n. And anyway, those are some of the structures that you look at in the work Dan and I were doing. That was part of the game, was to figure out what were the relevant structures. It turned out there were 10 of them, and I'll try to talk about that a little bit next time. Okay, so that's one thing. So another is, so that's our X. So there's, of course, a spectacular theorem of Jacob-Lurie along. In fact, the good apparatus of definitions is also due to Jacob-Lurie. And anyway, this spectacular theorem says that board n framed is the free symmetric monoidal infinity n category on a single dualizable, on one dualizable object, one fully dualizable object. Okay, so I'm going to talk about a simplified version of this that predates all of this, and so I'm not going to explain what fully dualizable means if you don't. I'm not going to explain that. Okay, so that's one thing. And so in other words, to give a field theory, Z from board n framed into some C is equivalent to, so the set of these, it turns out the natural transformations between these are always invertible. So these things correspond to what we call the space of fully dualizable objects. And this notation, this was designed to make kind of a pun here, because when this is vector spaces, fully dualizable means finite dimensional. And so that happens to stand for the same thing. Anyway, so that's one thing. And then in the case of a general X, imagine that what you have is the case of framed boardism at every point of X. And in the general case, you wind up, so for general X, you wind up with a bundle of spaces of fully dualizable objects over X, and the maps from that into C corresponds to sections of this bundle. Okay, so this is just to indicate that thanks to this work of Jacob-Lurie, we really do have a good theoretical understanding of topological field theories, and in some sense a good way of classifying them and computing with them. Okay, now. Now, it turns out that, and again, I'll say this more about this in the next lecture, but it turns out that in this condensed matter physics literature, that in fact the topological field theories that were coming up are what we call invertible field theories. So those are special kinds of topological field theories, but they predate the general ones. So invertible field theories so for there, Z of an M manifold is supposed to be not just a complex number, but an invertible complex number, so a unit complex number. And Z of an n-1 manifold is supposed to be a one-dimensional complex vector space. And in general, invertible field theory will be one that lands where the value of every object here is invertible under the symmetric monoidal structure. So that's the Picard space of C, which is not only has appeared in some of the top talks, it's like the title of this conference, isn't it? I mean, anyway, invertible objects in C. An invertible theory is one where it factors through all the invertible objects in C. And of course, that will factor through the quotient of this by the thing you get from this by inverting everything. So this is invert everything. Okay, so these invertible theories, they were studied and used before the general ones, and that's because a Picard a Picard infinity category, that's the same thing as the zeroth space of a spectrum. And so this is an infinite loop space. And this is an infinite loop space. And this map is an infinite loop map. So this just becomes a map of spectra in the sense of algebraic topology. And predating this, there's this spectacular theorem of Madsen-Weiss and of Galadius, Madsen, Tillman, and Weiss. That identifies this as the Thom spectrum of the bundle over X, which is of the virtual bundle, which is Rn minus V. So you take minus V, and then in order to have the points correspond to zero manifolds, you shift it up by n. Okay. So this is something that's susceptible to the analysis, to the methods of stable homotopy. And this right now can be an arbitrary spectrum. And in fact, even with suitably general X, and if you imagine we might pass to co-limits of theories like this, this can more or less be any spectrum as well. So the mathematical structure we're looking at the model, if you want, the sigma model, the Landau-Ginzburg model, whatever, the model that we're looking at is just the gadget that we want. Our basic model is just a map of spectra. So I won't give those names. It's just a map. Well, maybe I should. A map of spectra, maybe from something we'll call M to something we'll call C. Okay? It's just a map of spectra, and we're somehow trying to use that to model useful things. So that's like the Landau-Ginzburg model was a map from a stack to A1. In our case, our basic model of invertible topological field theories is nothing more than a map of spectra. But it becomes something because we're trying to we're imagining using it in different ways. Okay, so to fit this model to something that we're trying to model, we need to look at the physical situation and adjust. We need to use the feedback mechanism to adjust what these two things are supposed to be. So today, my goal is really to talk about how we're going to adjust this side. And in my next lecture, I'll talk more about what goes into adjusting this side. So let me look here at the time. I think I'm good. OK, so I should just check with the order. I'm supposed to stop when the big hand is on the 10? OK. I don't get any injury period for that long-winded introduction to... What's that? You get the injury period. OK. All right. I get the rule. I get it. OK. I'm with the... I'm going to give the rest of my talk with blue chalk then, so just to pay you back. OK, so that's our basic model. Now, what is C? OK, what should this C be? Well, so at this point, there's this dimension n of the theory, and we're working our way down from the top. There's the top dimension. There's what happened in dimension n minus 1. And I don't want n to be part of the game. So I'd rather shift everything so that n is 0 and just think about codimension. So codimension 1, codimension 2, et cetera. So in codimension 0, we're supposed to have the unit complex numbers. So that means that whatever this spectrum is, there's a map from pi 0 of C to the unit complex numbers. So pi 0 of C, I would shift everything up if I'm talking about an n-dimensional theory, and I'll just shift it so that this index here is minus the codimension. I'm coming down. OK, now there's a universal C with this property, right? So there's a universal such C. And it's the Brown-Kamenetz dual of the sphere, IC star, and it has the property that in spectra, a map from a spectrum, let's say E to IC star, that's just Hom of pi 0 of E into C star, the character group of pi 0 of E. And since C star is injective, that's exact, and by Brown representability, it's given by some spectrum IC star. And because of this definition, pi minus k of IC star is the character group of the stable homotopy groups of spheres. So the homotopy groups of spheres are in the game. Now, look, if there was something else in the physics that told us that, so whatever C is, it maps to this IC star. Whatever it is, it maps to IC star. If there was something in the thing we were modeling that told us it couldn't be arbitrary, then we might as well assume C is IC star. And there isn't anything, there's nothing I know of that tells us that's another condition on the target category, that the category in which the values of the field theory are taking place. There's nothing I know of that adds any conditions to this. So we should make an ansatz that the target category is IC star. Now, there's several things about this that are already interesting. So one is so let me say this better. So one of the things is that it has the right value at pi 0. So let's think about the structure. So I'll use this notation, underline M for the mth space of the spectrum. Okay, so this is the series of, these are the infinite loop spaces, and we're trying to understand something about what these mean. So IC star 0 is just the unit complex numbers. IC star 1, so that has two homotopy groups. That has a pi 0, which is Z mod 2, and pi 1, which is C star. And so it's not the category of one-dimensional complex vector spaces. This is modeled by Z2 graded one-dimensional complex vector spaces. Okay. And in fact, if you go back into the physics, that Z2 is important. This is the Z2 that's responsible for supersymmetry. And you need this Z2 if you're going to model electrons. It's the Z2 in the Fermi-Dirac statistics. So this Z2, which you can think of, turns out to be important, is also an indication that this is the right thing to do in the universal case. So one of the other themes in my lecture series here is that there tends to be only three values of this. There tend to be only 0, 1, and 2 tend to be the only three values of any of these things that we can really understand. So this has a nice model. This is modeled by the Brauer wall category of Z2 graded. So this is the Brauer wall category of Z2 graded simple algebras over the complex numbers. And I'll talk more about these things in my third and fourth lectures, but one of the themes here, well, so these are thematically what the conference is about, Picard groups and Brauer groups, and I want to, and these are still the only three instances where we can understand this kind of de-looping of groups of units and things. And a big mystery, this has been a mystery for a long time, is what this should be. We know that pi 0 is cyclic of order 24, so it has 24 objects, and whether that's even the right thing in nature, we don't know. And this has been a question I've been pushing for many years, and there's a lot of work that's been done on it. Andre Enriquez and Chris Douglas and others have ideas about modeling this with conformal nets. There's various ideas, but there still isn't really a successful model for what this space looks like. Okay. So I do actually not want to finish, in spite of bragging about how much time I had, I don't actually want to finish on that note. So let me just, just give me another couple minutes. I want to say something, I want to explain one other thing, and that is, this is already an interesting fact. I mean, we use this IC star, or some variations on it, which I'll talk about next time. We use that quite a bit and it's what Dan and I use, but that was just supposed to be, so that's supposed to be pick of some other C, where C is, we don't know. And I want to, so forgive me, I'm going to steal a little of time that you wanted for yourselves. But so this we have a definition of. It has a universal property, and it corresponds to a series of spaces that we would hope could be modeled by algebraic structure. So what's the analog here? We have a series of categories. C0, C1, C2. They're, in some sense, loop spaces of each other, meaning Cn is the n category of maps from the tensor unit in Cn plus 1 to itself. We know that the Picard group of Cn is supposed to be this. And we also know that, or this is just hypothetical, we're looking, one would like to have a collection of categories like this. The Picard group we sort of understand, and then what else do we know? We know C0 is supposed to be the complex numbers as a symmetric monoidal category. C1 is supposed to be Z2 graded vector spaces over the complex numbers. C2, we also have a good model of. This is Z2 graded, it's the Morita category of Z2 graded algebras. And beyond that, no one really knows what the CNs are. So I'm really about to wrap this up. So this is a major problem. What are these CNs? But it's one of those problems that, like, it's hard to actually make a clear mathematical question out of this. I'll give you an example of how something's not a mathematical question. So this, which we understood, this thing was defined by a universal property, right? This had the universal property that maps of a spectrum into IC star is Hom of pi 0 E into C cross. It's the character group of pi 0 of E. So we got this by knowing there was a natural universal property. And you might hope that this Cn is also characterized by some universal property. So for instance, so the question is, can C, which is this collection of CNs, be characterized by a universal property? And that makes you think, well, maybe we should go back and look at the C's that we understand and ask, do those have a universal property? And the answer is sort of yes. Yes, we don't know, right? So C1, that has a universal property. And I'm going to put it like this, and that's due to Deligne. And Deligne proves that this C1 is algebraically closed in some sense, and that if you have a category, a symmetric monoidal category with some finiteness properties, there's enough functors to C1 that you can recover that category as, so that collection of functors forms some kind of a group, and you can recover your category as representations of that group. So this has to do with Tanaka duality and conditions under which you can write a category as representations of a group. But I just want to emphasize that this involves some finiteness conditions. And I was giving some talks at Northwestern last spring and advertising this point, and Theo Johnson-Fried was in the audience. And he and I got wondering, you know, there is one more example of this we know, namely C2. And we got and so this is a work in progress, but we're trying to understand whether this category C2 has a similar universal property. But right now it's kind of up in the air, and you discover as you start getting into this that the question really here isn't, does this have a universal property? The issue is really trying to understand the appropriate finiteness conditions. So there's an ill-defined mathematical question that comes out of trying to model the physics, which is, what is to seek this hierarchy of categories, but to try to understand what they aren't arbitrary. I don't think it makes sense to characterize some arbitrary family of categories with these properties and these Picard spaces, but rather to find ones with that there's a finiteness kind of condition that we don't know how to ask for. And I'm hoping, or Theo and I are hoping that we'll get closer to understanding it by trying to understand the universal property of this Morita category. Okay, I apologize, I've gone over time. I'll pick these themes up tomorrow and over the next couple lectures. Thank you.
Time for one really good question.
Yeah.
So, you know the property of the C0 factor as by this context?
Yeah, I was sort of hoping no one would think to go backwards. I don't know. So you could think of, I think you're supposed to think of it like this. A symmetric monoidal zero category is like a ring, and you're looking at ring homomorphisms to the complex numbers. So the question is, what kind of rings can you get out of if you know the complex points of the variety, right? So that actually also tells you, I guess that's like butt dialing. But anyway, that also tells you, right, simple algebras, rings that are products of rings. There's a finiteness condition that tells you, I can completely recover certain rings from their points, and other ones I can't. And so that is it's a good example. I should have thought to mention that tells you, you don't really expect to get an arbitrary ring out of all of its ring homomorphisms to the complex numbers, but with some kinds of finiteness conditions, you can hope to. So yeah, and in Deligne's work and all that theorem about Z2 graded vector spaces being algebraically closed, it's very much the spirit of thinking of symmetric monoidal categories as being like commutative rings, and those as being like the points.